Welcome to this explainer. Today we are popping the hood on internet security. We interact with the digital world literally every single day, but we rarely stop to actually understand the sophisticated, multi-layered digital fortress that is actively protecting our data. So let's break down the technical architecture of that fortress, piece by piece.
Okay, let's dive into this. To demystify complex cybersecurity, we're going to explore 6 specific defensive layers. 1. Mapping the threat landscape. 2. Encrypting data in transit. 3. Public key infrastructure explained. 4. Advanced firewall technologies. 5. Hardening system access. And 6. Isolating your digital identity.
Section 1. Mapping the threat landscape.
Now, before we build our defenses, we really need to understand the specific technical threats out there, right? Take ransomware, for example. This is a nasty piece of malware designed to literally lock you out of your own machine. It encrypts your system and your personal info, basically holding your data hostage until you pay a ransom fee to cybercriminals. It is incredibly common, and it's very often delivered via malspam, those unsolicited emails hiding malicious attachments or links. Because ransomware completely locks down your data, it's a critical threat that proves exactly why we need the layered defense architecture we're building today.
But sometimes threats are a lot quieter. If your machine is compromised by spyware, you might start noticing some immediate technical symptoms. We're talking programs suddenly dragging and opening slowly, relentless pop-ups, constant error messages, or maybe a brand new browser toolbar that you definitely didn't install. Even your browser's default search engine or homepage changing automatically. That is a massive red flag. Pointing out these technical symptoms is crucial, but our real goal is to stop these infections before they even reach your machine, starting right at the transit level.
Section 2. Encrypting data in transit. Let's move to the perimeter of our digital fortress and see how this all builds together. When you're sending info across the internet, looking for that HTTPS in your browser's address bar is absolutely vital. Why? Well, on a standard HTTP connection, your data requests and responses are just floating around in plain text. Anyone intercepting that traffic can read it, but HTTPS is an entirely different story. That S stands for secure. It combines HTTP with specialized cryptographic protocols to encrypt all your transmitted data. It is literally the difference between sending an exposed postcard and a heavily armored transport vehicle.
And the actual engine under the hood of HTTPS? That's TLS, or Transport Layer Security. You can think of TLS as digital passport control. When your browser connects to a site, TLS uses a digital certificate to verify that the server is exactly who it claims to be. But how do we know the certificate isn't fake? That relies on a CA, or Certificate Authority. Trusted bodies like VeriSign or Entrust act as the guarantors, proving the site is legal and reputable before your browser agrees to share a single byte of your data.
Section 3. Public key infrastructure explained.
So, the crucial point here is that TLS relies on something much deeper, a highly secure mathematical handshake known as PKI, or Public Key Infrastructure. PKI uses a brilliant concept, a pair of keys, one public and one private. These keys are digitally signed by our trusted certificate authority to guarantee 2 things: that the sender is reliable and that the message content is totally unaltered. This is the engine of asymmetric encryption. It's the exact mathematical architecture that makes secure online banking and e-commerce possible. Let's make this abstract cryptography concept incredibly tangible by walking through the exact step-by-step data journey. Imagine user X wants to securely communicate with user Y. First, X sends their public key over to Y. Then, X writes a message, encrypts it using their own secret private key, and sends it off. When Y receives it, they use X's public key to unlock it, proving without a doubt it came from X. Now, to reply securely, Y writes an answer, encrypts it with X's public key, and sends it back. Because it was locked with X's public key, literally only X can open it using their private key. It's an amazingly foolproof system of digital locks and keys.
But wait, this actually raises a really fascinating question. We've just perfectly encrypted our data streams, right? But what if a cybercriminal uses that exact same encrypted connection to send a malicious file directly into your network? If the data is encrypted in transit, how do we actively guard the network gates and stop malicious packets from just walking right in?
Section 4. Advanced Firewall Technologies.
This is where firewalls come in as the critical first line of defense between your intranet and the wild internet. Now, what's really interesting about this is just how highly configurable these rules are. They don't just blindly block everything, they check every data packet against specific rules. They can block traffic containing specific content keywords, they can reject data from known malicious domains or suspicious IP addresses. They'll even block traffic trying to sneak in through unauthorized port numbers. Network admins use a clever mix of blacklists and whitelists to manage exactly what data flows in and out.
But threat tech moves fast, so firewalls had to evolve. Early ones used stateful inspection, which basically filters packets based on the current status of the connection, checking if the communication handshake looks legit. But modern threats, they require deep packet inspection, or DPI. Think of DPI as a digital bouncer. It doesn't just check the ID on the outside of the packet header, it actually opens it up and pats down the entire contents of the packet. That is how we accurately find disguised, deeply hidden viruses and Trojans.
And today, these advanced technologies are usually bundled into Unified Threat Management, or UTM. A UTM is a real game changer. It represents the evolution of network security by bringing things like next-generation firewalls, application management, and active intrusion prevention all under one single roof to create a massive, centralized defense system.
Section 5. Hardening System Access. Let's transition to the inner vault of our digital fortress, protecting the local machine. There is a core philosophy from our source material to remember here. Privacy depends on the ability to control who has access to your information. It sounds super simple, right? But it's absolutely profound. Because honestly, all the transit encryption and deep packet inspection in the world fails completely if an attacker can just guess your password. One technical way your operating system helps control this access is through tools like User Account Control, or UAC, which you'll find in Windows. Think of UAC as an internal alarm system. It forcefully requests your permission before any major system changes happen. This is incredibly crucial because it stops intruders from quietly exploiting administrator privileges in the background to add new users or change passwords without you ever knowing.
But your OS can only do so much. We have to actively secure our own credentials. Implementing these 3 steps actively fortifies your daily online life. First, use a password manager. They store your data in a secure container file, encrypted with a random key, all locked behind one master password. Second, avoid credential reuse. If you define a unique random password for every single site, a breach at one company won't cascade into all your other accounts. And finally, 2-step authentication. By requiring a secondary PIN code sent to your mobile device for every single login attempt, even if someone steals your password, they are stopped dead in their tracks.
Section 6. Isolating your digital identity. For our final layer, we need to talk about masking your physical footprint when you're interacting with external, untrusted environments. If you are sitting at a coffee shop using free public Wi-Fi, you have zero guarantees about connection security. Someone at the next table could literally be intercepting your traffic. That makes a virtual private network, or VPN, a technical necessity. It establishes a secure, encrypted tunnel right through that untrusted network.
We can also isolate our financial identity. When you're buying things online, providing your actual credit card number to a server introduces a ton of risk. Virtual credit cards minimize your personally identifiable information by generating a temporary trackable number. It basically acts as a firewall for your actual credit card, completely isolating your real financial data during e-commerce transactions. But what happens when the technical security of the companies we trust just fails? Because data leaks absolutely happen. Well, when technical security fails, regulations like the GDPR exist to step in. The General Data Protection Regulation gives users the legal right to view what personal data is collected and, more importantly, the power to request the removal of that collected data from vulnerable databases. It's designed to limit data hoarding and acts as the legal layer of our digital defense.
We have covered some truly incredible ground today in this explainer, from asymmetric encryption keys to deep packet inspection. But I want to leave you with this final provocative thought. Knowing the advanced, multi-layered architecture required to actually secure the internet, are your daily online habits helping build up your digital fortress, or are you accidentally leaving the front door wide open? Take these technical concepts, apply them to your own privacy, and take control of your digital life. Thanks so much for joining me, and keep learning.